Okay. Okay. All right. So we are now recording this meeting. All right. So what I'm going to do now is begin with the basic ideas of this course, just as a refresher. Okay. All right. Now, one of the things that we do is we use these circuit diagrams to, describe and in a schematic way, an electric circuit. As I've mentioned, I keep stressing the models can be used for other things. In fact, when you take system dynamics, I know that Professor Garcia is going to show you circuit diagrams, even though you're not going to build any circuits or anything like that. It's just because they are a really good abstract way to describe systems in general, and it's something that he knows you'll have seen before. Okay, now when we look at circuits, one of the basic rules that we work with is Ohm's law. Okay, Ohm's law, where we're describing the relationship between voltage and current in a resistor. So we have a resistor with a resistance R, okay, and then Ohm's law is assuming that you have a voltage change across a resistor where you have a drop as you move from left to right and the current flows left to right through the circuit. So assuming that the current is entering the positive terminal, the relationship between the voltage and the current is V is equal to Ri. Okay, so that's Ohm's law. It only applies to resistors. Okay, you can't use Ohm's law for a source, of current source, a voltage source, an inductor, capacitor. It only works for resistors, but it's super useful. Okay. The other thing that I want to draw your attention to is Kirchhoff's current law, where if you have a junction or a node and you have multiple wires attached at that point, because that's what the junction is, you have currents flowing into and out of the junction or node. Okay, and you can mark them any way you like, but let's say we have a node like this, and I'm going to call this node X. Okay, so at node X, okay, you see that you have I1 and I2 flowing in. Is this big enough? Can you see this all right?
Yep, it's great. Yeah.
Okay, so you have I1 and I2 flowing in. You have I3 and I4 flowing out of this junction, the way that they're labeled. So the Kirchhoff's current law says that the sum of the currents entering the node is equal to the sum of the currents leaving the node, which is pretty intuitive. You can think of them as fluids flowing into this point, this junction. You don't have any of the current pooling there, right? There's no deficit or pooling. You have conservation of energy. So I1 and I2 are flowing in. The sum of those currents entering the node is equal to the sum of the currents leaving the node. Okay. And so this is a useful relationship because if you know all the currents but one, you can solve for that unknown current, right? Okay. Then we have Kirchhoff's voltage law. Okay. And that one has to do with voltages, obviously. And the idea here is that if you can identify, say, let's say we have a bunch of elements, okay, and I'll just put them in boxes. It doesn't matter what they are, okay, I'll call this element A, this one B, this one C, like that, okay. They could be connected together, okay, and if I know the voltages across, let's call this VB, this one VA, and this one VC, like that, okay. The sum of the voltages around a closed path is equal to 0. Okay. You probably remember this, but I'm just reminding you of this, okay? And these are like the basic rules that we use to do circuit analysis. So when I look at this and I can identify a path around which I know all the voltages, okay? So I can say I'm going to move clockwise around this path and I'm going to add them all up. Okay, and this is the one where it's a little bit less intuitive, right? So I just have to pick a place to start. So I usually start in the lower left-hand corner, and I see that I have the negative terminal here on this element is marked with the minus sign. The positive terminal here is marked with the plus sign. So as I move along this path, there is actually a rise of voltage. This is the reference point. Okay, down here is my reference point, and I say, from this reference point, I rise by VB volts, right? So I'm going to call that a positive voltage. And then I come up here. Now the wires we assume are perfect, right? That you don't see any markings of voltage along those. And so we don't worry about what's going on along the wire. Then we come to this one and you say, okay, now I'm at VB volts above the reference point down here. Then when I pass through this element, I drop my VA volts because I start at the plus terminal and I go to the minus terminal, okay? So that means I'm going to express that change, moving me over here as minus V sub A, okay? And then when I get here, okay, again, I'm entering the positive terminal, exiting the negative terminal. That's another drop, so I write that as VC. I get down here, okay, then to get back to my starting point, I just go along this wire, but there's no voltage change there, so I'm done. Okay, those are all the voltages, right? So that is the equation that describes the voltages around that path, okay? And so if I know all but one, I can get the one I don't know, right? Now, this particular case, the path that I chose, actually everything's connected with a wire, but they don't have to be. As long as I know the voltages between 2 points, that's good enough. So, for example, I could do something like this, where let's just say I have an open here, okay, and then I have A, and I have C here, okay, like this, and I happen to know that the voltage between these 2 points, which I can measure, is VB. Even though there's no element there, there's no wire there, this is still VA, and this is VC. I can still move along this path, okay, because I know what the voltage is between these 2 points. Okay, so they don't have to be attached. You just have to be able to trace a path where you know all the voltages. Okay, so that would be described using the same equation as down here. Okay, do you have any questions so far?
Oh, that's pretty clear.
Okay, good. Okay, all right, now I would like to do a problem. One of the things that I told the class was I wanted you guys to know how to do what's known as nodal analysis. You may have heard me talking about that. There are a lot of analysis techniques. That one is the one that is the most widely used. You can solve a lot of circuits using nodal analysis. There's mesh analysis as well. There are other techniques, but nodal analysis is one that works on a wide variety of circuits. And so that's one that I want to go over now with you. And that's the that's the one that I want to do now. So I'm going to do an example because it usually works best if I do that. Let's say we have a circuit that's got this layout. Hang on. It's got a current source that, oops, that's not a current source. Sorry. Okay. It's a current source here. That's 14 amps. Okay. And then I've got a resistor here that is 2 ohms. I've got another one up here, horizontal, that's 1 ohm. I've got a 4 ohm resistor here. And then I've got 7 amps here. Okay, so that's what the circuit looks like, right? So it's got these 3 resistors here. It's got the 2 current sources, okay? And let's say that I would like to know, okay, we're going to use nodal analysis to do this, okay? And the way that that works is we first identify where all the nodes are, okay? So can you tell me where any of the nodes are?
Yeah, so if you start at the 14 amp current source, it would be so in between the 2 ohm resistor and the 1 ohm resistor, that corner there. Yep.
Here. Okay. Okay.
And then going through that 1 ohm resistor where the 4 ohm resistor and the 1 ohm resistor join.
Here.
Yes.
Okay. Anything else?
Is there one on the bottom as well?
Yep. Where on the bottom is it?
Could it be anywhere? Or if you go through the 4 ohm resistor,
Here.
would it be there? Yeah.
Okay.
And
Is
then
that it?
going through the 2 ohm resistor right there.
Here. Okay.
Yeah.
So 2 nodes at the bottom?
Yes.
Okay. So a node is where we have the wires joined together, but electrically, these 2 points are identical because you see this is just a wire.
Yeah.
You could make, since the wire is perfect, you could make it super short. If you shrank it down, think about what would happen. You shrink it down to nothing.
Yeah.
Right.
It'd be one.
It's,
Okay.
yep. Yeah, you can't do that at the top because there's a resistor there, right? Those are electrically different. There's some kind of, we assume there's a change in voltage here. Since there's no change in voltage along here, we can consider that to be a single node. Okay.
Okay.
Okay, so yes, there are 3 nodes in this circuit. And so to do nodal analysis, first you identify the nodes, and then you gotta select one of the nodes to be a reference node. Okay, so generally what I do, you can pick any one you want, but I usually pick the one on the bottom. Okay, because everything is in reference to the bottom. You say, how many volts is it different from the bottom, right? So you just go ahead and use it as a reference point. And then you can label the other nodes. This is, we can call this 1 and this 2. Okay. And the voltage at this point at node 1, we say that node 1 is V1 volts above the ground, and we can say the voltage at V2 at 2 is V2 volts above ground. So all the voltages that you specify here aren't absolute. Their voltage is always in reference to something. Okay. So in this case, the V1 will be in reference to ground. Now, it's also the voltage across that 2 ohm resistor here.
Okay.
Okay. And here V2 is the voltage across the 4 ohm resistor. Right? Because its voltage is between 2 points. It's not an absolute value. Okay, so if we want to know what V1 and V2 are, let me get another color. Then what we do is write equations at the nodes 1 and 2 here. Okay, so we can write an equation at node 1. Okay, and we remember that when we were using Kirchhoff's current law, we say the sum of the currents entering the node equals the sum of the currents leaving the node, right?
Yes.
So what we can do at this node is we can draw all the currents entering and leaving the node. Okay, so we have 14 amps coming in, right? So I'm just going to put an arrow here showing that that current is entering. We know it is because here's this current source, right?
Yes.
The other currents, it doesn't matter what direction we put the arrows in, but I usually have currents leaving. So I'm just going to draw them like that. Okay, and just say at node 1, I've drawn the currents. I have all 3 of the wires are marked with arrows. And I say, okay, the sum of the currents entering the node, there's only one current entering the node, and that's 14 amps, right? 14, yes. Okay, is equal to the sum of the currents leaving the node. And so here I've got a current leaving the node going straight down, okay? And so I want to describe that current, okay? And this is the part now, you notice that we have we have a current here, and it's going through a resistor, right? Yes. Initially, I don't remember how much of this you remember or how much you've done. I'm just going to label this as a current. Okay, I'm going to call it I1 just for the moment. Okay, so I'm going to say it's I1. Okay. And then I'm going to say I have I2 leaving the node horizontally going to the right. Okay, so I got I2. Okay, so 14 coming in, I1 and I2 leaving. Now, the next step is to express each of these currents in terms of the node voltages. Okay, and this is something you're going to probably have to practice because you have to remember how this works. So the way that it works is, okay, first of all, I'm just going to put the 14 in here, right? I1 is the same as the voltage across this resistor divided by the resistance by Ohm's law. Okay, it's V divided by R. Okay, what's the voltage here? It's V1. I could say it's V1 minus 0 because it's V1 minus this current, this voltage down here we're calling 0. Right, I'll just put a 0 here, okay? Divided by this resistance, which is 2 ohms. Okay, there goes my pen. Okay. Have another green one. I wanted to try to keep the colors the same. Maybe I have another green one. Okay. So I used Ohm's law to write that. Okay. And then to write I2, I say, okay, the voltage across this 1 ohm resistor is V1 minus V2. Okay. Now, it's easier to see, I think, that this voltage here, V1, is V1 minus 0.
Yes.
This one here, it's V1 minus V2. You see the direction of the current going through here. I mean, I could prove this to you, but that I'm telling you that's what it is, okay? That the voltage across here, this specific voltage here is V1 minus V2.
Okay.
Okay, so, and then you divide by the resistance. So we've gone from this line here, where these are currents, right? 14 amps. This is a current, this is a current. And then down here, I'm leaving this as 14 because I know what it is. It's just 14, okay?
Yeah.
But here, I don't want to use currents anymore. I want to use voltages to describe what's going on here. So because this current is flowing through a resistor, I can write it as V1 minus 0 divided by 2. Okay, the voltage over the resistance. I can do a similar thing here, the voltage over the resistance. Okay, so now I have this equation. And then I want to clean it up a little bit, okay, because I've got some fractions in there, right? So what I'm going to do next is multiply everything by 2. So on the next one, I'm going to have 28 equals V1 plus 2 times V1 minus V2. All right. And then I clean it up a little bit more. I got 28 equals 3V1 minus 2V2. Okay, so that's my basic equation for node 1. Okay, and where did I get that? I got that from Kirchhoff's current law. All right. So I use the currents, but I express them in terms of voltages when necessary, when currents are flowing through resistors. Okay, so that's node 1. Now, if I go to the other node over here, node 2, I see that I've got 3 wires here also, right? So I've got 7 amps flowing out. So I'm just going to put an arrow like that showing, okay, that's the 7 amps leaving. And then the other currents, well, we've got I2 coming in, right? Because I2 flows through this resistor and then it enters this node. Yeah. And then I'll just put this current leaving like that. Okay, so I'll just put this one in like this because that's I2. So this is I2, and I'll write this one as I3. And then this one is 7 amps leaving, okay? So at node 2, what do I have? I have a current coming in, which is I2. And then I have I3 leaving, and I have 7 amps leaving, okay? Yep. So it's a similar sort of situation where I2 is flowing through a resistor, I3 is flowing through a resistor. So I want to rewrite those using Ohm's law. I2, the current entering the positive terminal, right? Because Ohm's law assumes you got the positive terminal here. It's V over R. Okay, so what's the voltage there? The voltage across here is V1 minus V2. And then R is 1 ohm. Okay. And then I3 is V2 minus 0. V2 minus 0 divided by 4 ohms. Okay. And then I have 7 here. Okay, so now I have this equation. And like the previous node, I want to clean it up so I don't have any fractions. I'm going to multiply every term by 4. So now I have 4 times V1 minus V2 equals V2. Oh, sorry. Yeah, no, that's right. Okay, plus 28. Okay. All right. And then let's do a little bit more. 4 V1 minus 4 V2 equals V2 plus 28. 4 V1 minus 3 V2 equals 28. Oh, I made a mistake. No, that's right. Sorry, I thought I made a mistake. That's right.
Would it be 5v2?
Is it 5?
Minus
Oh, yeah,
5v2?
you're right. I messed up. Thank you. Thank you. I was looking at my notes. I'm like, wait, there's a 5 there. Thank you. I appreciate that. Okay, so that's the equation. All right, now going back, I want to go back because I realized I didn't explain this particularly well. So this business up here of Ohm's law here, right?
Yeah.
Okay, so really, if I just redraw this over here and I put in those circles like I had here, right? And I have my voltage here, V, and I have I coming in, and here's R. And I told you that Ohm's law says V equals RI, right?
Mhm.
If I label this as V1 and this as V2, then this voltage V is equal to V1 minus V2. That's what I'm basing this on, okay? So when you're substituting, you have to pay attention to what direction the current is flowing in, okay? And so you say, all right, whatever, when the current is flowing through a resistor, the way that I get the voltage across that resistor is I say it's the voltage at the node that it enters minus the node that it exits.
Okay.
All right, and that's going to be something that it will just come to you easily when you practice, okay? So that's why I'm going to suggest that you go over this example yourself.
Yeah.
Later. I'm going to assign you some practice problems also for you to go over, okay?
Okay.
All right, so, well, there's the, okay. All right, so back to this. We have these two equations, and then after this, it's an algebra problem, which hopefully I won't make a mistake on again. So when I find when I get something like this, you know, you have to do some kind of substitution, right? And it's when you inspect it based on the coefficients, it's not simple to see what it's going to be, right? Did I do this correctly? Let me just make sure I did. Yeah, I did do it correctly. Okay. I think I did it correctly. Let me see. Yes, I did this correctly. Okay, so what I can do then is to combine them. I'm looking at it and I'm thinking I'm probably going to want to add them together somehow. So, I mean, there's different ways that you can do this, right? But what I'm going to choose to do is I'm going to multiply this equation in green by 4. Okay, and the reason I'm doing that is because I want to make this coefficient 12.
Okay.
And then I'm going to do a similar thing to this one. I'm going to multiply everything by 3, and then I'm going to make this coefficient 12 also. Okay.
Gotcha.
So then I'll combine them, and then I'll be able to eliminate the V1 and solve for V2. So when I multiply everything on this one by 4, I'm not going to multiply it out. I'm just going to write this as 4 times 28. Okay. And this is equal to 12 V1 minus 8 V2. Okay. And then this one over here, when I multiply everything by 3, I get 12 V1 minus 15 V2 equals 3 times 28. Okay. All right. I think what I'm going to do now is multiply this second equation by -1 because I'm going to add them together. When I do that, I get minus 12 V1 plus 15 V2 equals minus 3 times 28. Okay. Now, having done that, I'm going to take this equation here and I'm going to add it to this one up here. Okay. And when I do that, I'm going to get, well, I'll put the minus 3 times 28 over here. Minus 3 times 28 equals minus 12 V1 plus 15 V2. Okay. And then I combine them like this. So on the left-hand side, I'm going to get 28. Okay. Equals, these 12 V1s go away because they add to be 0. And then I get 7 V2 here, right? I get that V2 is 4. Okay. And then just a reminder, I really like integer answers. I don't know about you, but it's kind of like, okay, I got an integer. I mean, is that realistic? No, I mean, like when you're actually building circuits, they're usually not integer answers. But when we're doing problems, it's good to have integer answers because then you say, okay, I probably did this correctly, right?
Yeah.
Right. So I try to do that, you know.
That's good.
So if you get some crazy decimal or whatever, it probably means you made an algebra mistake someplace. Okay. But you know,
Okay.
if you can't find it, you just keep going. Okay. Anyway, so 4 volts for V2. Okay, and then V1, I'm going to come down here because I've got a little bit of space down here and finish it up. Okay, let me take this green equation and sub in the 4 for that. So 28 equals, this is not the right pen, 28 equals 3 times V1 minus 2 times V2, which is 4. So 36 equals 3 V1. V1 is equal to 12 volts. Okay, so those are the voltages. And then once you have those voltages, you can get anything you need, okay, in the circuit. Like, let's say, for example, you want to know the voltage across the 1 ohm resistor. Well, it's V1 minus V2, right?
Yeah.
And that's 4 minus 12, which means it's minus 8 volts. That just means the polarity is opposite of what we thought it was across this resistor. It means the current's flowing the other way, actually.
Okay.
You can get any of the currents that you need. You can get I1, for example. I1 is equal to V1, which is 4, divided by 2 ohms. So it's 2 amps. So you can get anything, right? So that's why solving for node voltages is a useful thing to be able to do. It applies to a lot of circuits very generally. Okay. Do you have any questions on this at this point?
No, that was clear.
Okay. All right. So what I'm going to do then, as I said, is I'm going to give you some chances to practice this. Okay. I'll give you some homework problems for that. Okay. All right. Now I'm going to now do another. Now you'll notice that this particular example that we did, the sources were current sources. I want to do an example with a voltage source in it. Okay. Let me get this. Which one did I want to do? 4.2. Okay. So let's say that we have a circuit that looks like this. It has a 16-volt source over here attached to a 2 ohm resistor here. It has a 9-volt source here, 3 ohm resistor below it. Okay, those guys are attached like that. 6 ohm resistor up here. And then there is a 6-volt source here. So lots of voltage sources, okay? All right, and we want to do nodal analysis to this one as well. So identifying the nodes here, right?
Yep.
Really, it's any place you have stuff joined, right?
Yep.
Here, 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 and then down here. Okay. All right, so more nodes for this one. Now, this one, we'll call that one ground, have it be the reference point, okay? And then we label the voltage sources A, B, C, and D, okay? All right. Now, remember that the voltage at A is the voltage with respect to ground.
Yeah. Okay.
So if you look at this, you see it's 16 volts, right? Because you go along here and you say, that's my reference point, then I rise by 16 volts going through this source, okay? I get to this point and that's A, okay? So the voltage at A is 16 volts, okay?
Okay.
Does that make sense to you?
Yes.
Okay. You can do a similar thing over here, right? Because you also have a voltage source. I'm down here. I rise because of the polarity of the source by 6 volts to get to C. So VC is 6 volts. So I have 2 of these sources already all set, okay? Now, if I'm here at point D, I don't know what that voltage is, but I know that when I start at point D, whatever that voltage is, and then I go up this way, I rise by 9 volts to get to B. So that tells me that whatever the voltage is at D, I can add 9 volts to it, and then I will have VB. Okay?
Yep.
All right. Now, we've done that, and now what we'd like to do is solve for the unknown voltages. So we already know two of them. We don't know what VD is. We don't know what VB is, but we know the relationship between them. Okay. So proceeding and using Kirchhoff's current law. All right. So we don't need to write an equation here at node A because we've solved for what it is. Same for C, but let's go to B and work on that one. Okay. So if I'm at B, I can draw little arrows here. Let's just say I have them all leaving. Okay. At node B, I say, okay, I have this current here. I'll call it I1, and I have I2, and I have I3. Okay. I have I1 leaving. I have I2 leaving. I have I3 leaving, and they have to sum to be 0, right? So if I say I want to express I1 in terms of Ohm's law, I can do that because the current is flowing through the resistor here. I can say that I1 is VB minus VA, because that's the direction the current's flowing in, right? Divided by the resistance, which is 2. Okay. Then I go to I2 and I say I've got VB minus VC divided by 6. Again, I2 is flowing this way. So I take the tail, I say the voltage there, VB, minus the other voltage, VC. Okay. Then I go to I3. Okay. Now, I can't use Ohm's law here because that's a source, right?
Yeah.
So this is a problem. I can't write it. I have to use I3 because I don't have a way to describe the relationship between voltage and current, how it's affected by that source. Okay. So you can't use nodal analysis in this way when you have a source. It's great for a situation like this. At node A, I know exactly what the voltage is because here it is. You know, I can describe it from ground up here. Same for node C, but then I have a problem here. So I have to use a slightly different approach. I can enclose any part of the circuit and call it a node. We usually talk about nodes as being just where two elements are joined, where the wires come together, right? But I can enclose this here, the source, like this. And then I call everything inside that blue circle a node. It's called a supernode.
Okay.
Okay, this is what happens when you have a voltage source inside a circuit and you're trying to write a nodal equation and you run into this problem. Like here in these cases, it's fine, but here it's not. Okay, so what I do now is I say, all right, instead of treating the node as like one of these little dots, these little pink dots, now I have to think of this thing as the node. And I say, okay, this blue thing has 3 wires sticking out of it, right? It's got the wire here, it's got the wire here, and then it's got a wire down here. Okay, so I can write equations. I just say, all right, I'm going to put a blue arrow here, blue arrow here, blue arrow here, and write an equation for the supernode. I can still refer to these voltages, VB and VD, but I can't write anything that talks about what's going on inside the node. It's what's coming out or going into the supernode. So up here, I say, all right, well, the voltage here is VB. So VB minus VA over 2, just like before, there's a current that's flowing out that way. I can describe it using this. Same thing for this one over here on the right. There is a current flowing to the right, VB minus VC divided by 6, okay? And then now I'm going to talk about the current flowing out down here, okay? That current is VD minus 0 divided by 3, because that is a resistor, okay? And that has to equal 0. The sum of the currents entering or leaving a node, as I define a node, has to be 0. So Kirchhoff's current law still holds. It's just that now I've enclosed a bigger thing and I'm calling that a node. And I only do this when I have to. And it's only in these cases where I have a voltage source that I can't describe in another way, okay?
Okay.
So now I have a supernode and I don't see any currents in here. I just see voltages, right?
Yeah.
And that's great. And I already know what VA is and I already know what VC is, right? So I can just put those in. I can say VB minus 16 divided by 2 plus VB minus 6 divided by 6 plus VD over 3 is equal to 0. Okay, so I've got a nice equation there. And I can multiply everything by 6, right? So
Yeah.
I can do that. Let's see. What do I do? 6. So that's going to be 3 times VB minus 16 plus VB minus 6 plus 2 VD is equal to 0. Okay, so that's all set now. And I have this equation, which has VB and VD in it. And I have this equation up here. I have to have a second equation, right? There it is. Okay, so those are my 2 equations and 2 unknowns. All right. Okay, so I'm going to let you finish this, okay? Actually, I'm going to suggest, just like for the previous example, that you go through this again yourself, okay?
Okay.
Like, go back, watch the video, stop it when we get to where I drew it, and then do it yourself, and then follow it through, okay?
Okay, sounds
Great.
good.
Okay, do you have any questions on this one?
No, I don't think so. I think the difficult part for me is just going to be recognizing when to use that super node and use just identifying when it's needed and when it isn't needed. But
Yes. Right. That's why I deliberately did this example, because you see that it has voltage sources in it. So, but some of them you could directly write what the voltage is, right?
yes.
It was helpful to have this voltage source here. This one's not so helpful, right? Because you have to use this other alternative. So it'll become clear to you after you label the nodes what you'll have to do. Okay, because you notice that I started to write an equation at node B, and then I realized I couldn't do it. And that was what prompted me. Okay.
Okay.
Yeah. So that's the purpose of the illustration. All right. Okay. So what I would like to do is, let me just tell you where I'm going with this. Okay. I would like to give you some problems to do on this particular topic. It would be nodal analysis with current sources, with voltage sources, a few examples for you to work through.
Okay.
And then I would like to give you the opportunity to ask me questions on anything that you're having trouble with. And then I would like to give you a quiz on this, okay?
That's good.
On this topic. So here's what's happening, okay? I'm going to be in Bismarck through Tuesday.
Okay.
And then I have previously scheduled travel starting Wednesday for about 10 days, unfortunately. So, which is, so what I would like to do is meet with you. Okay, here's what I like to, here's what I'm thinking. Okay, I want to give you sufficient time to do these examples. I'm not going to give you a whole ton of them, but I'll probably give you like 5 or 6 problems to do. Okay. I know you have other things going on. Are you doing any other courses now?
I'm still kind of working through that. Probably, I don't know if I'll be able to do all of them, but I think I'll be able to do one more. Just
so
to
this
not
one and another
overload.
one?
Yes.
Okay, all right. Okay, so you'll be doing just mine and one other. Okay, that's good to know, because I don't want to overwhelm you. So I would like to meet with you early next week.
Okay.
Do you think you could meet with me on Monday? Would that be possible?
Yep, that works.
Yeah, maybe in the afternoon. Would that give you enough time, you think?
Yeah. Yeah, that should be
Okay,
good.
great. Okay, so see, I'm thinking that I want you to email me, and please email me over the weekend. It's not a problem at all. Not at all. Just if there's anything you're struggling with on these problems, just email me and say, I can't do this, and I will meet with you on the weekend. It's fine. I have my document camera, whatever. Okay. Because the next time I meet with you, I would like to be able to give you a quiz like we did in class. All right. What I'll do is it'll appear on Canvas for you. And then you just go ahead and write on paper, like your answer, you don't even have to print it. You can just write on paper and then take a picture of with your phone, take a picture of the page that you did. Okay. And then you can email it to me, or you can upload it. Maybe I'll just make it so you can upload it. Whatever is easier for you. It doesn't really matter. Okay.
Yeah, that works.
So I would give you like 15 or 20 minutes on Monday, or I can just have, if you want, I can have it appear on Monday, and you can do it Monday before we meet on Monday, because I would like to give you another lecture on Monday afternoon on the next topic. Okay.
Yeah, that works.
Okay, so I will set up a homework for you. And I will plan to set the quiz. Do you want me to make the quiz available just starting Monday? I could put it Monday. You could do it in the morning. I mean, I don't know what,
Yeah.
do you want, will you have enough time Monday morning to do it?
Yeah,
Before
that'll
we
work.
meet Monday afternoon? Okay, do you want to meet at like 2 on Monday? Would that
Yeah,
be
we
all
can
right?
do that.
Okay. Okay, so I'll set the quiz to appear Monday at midnight or whatever. Okay, like Monday, 12 a.m. Okay, and so you'll have any time, before 2 p.m. to complete the quiz.
Okay.
And then take a picture of it, send it to me, and then we'll meet again on Monday. And I'm going to go on to the next material at that point, and it's going to be frequency analysis of circuits. So we'll do that. We might meet a bit longer on Monday, and then I'm going to give you some stuff to do, but also some stuff to read. Okay, because I'm going to have you work forward, give you exercises to do and reading to do in the textbook while I'm away. All right.
Okay.
And then we can communicate by email. I'm not going to be able to meet with you doing a video call. I'm not going to have access to the internet. I'm going to Canada. I'm going out in the woods with Patrick. There's no internet at the place we're staying. I will have my phone, so I will be able to read email, but I won't be able to do a video call with you. I'm really sorry.
No worries.
So if we meet on Monday, that'll work. If it needs to push off to Tuesday, we can do that. But then Wednesday, I'm gone. Okay. And then, okay, then we can talk again the next time we meet about what you'll do during this time that I'm going to be away and how we'll handle it. Okay.
Awesome. That works.
Okay. All right. So I'll put some homework on there for you. You should see it in the next few minutes, and feel free to contact me anytime. I'm going to give you my cell phone number also. I want you to feel free to text me. Okay, hang on. I'm going to go back to my camera. Here we go. Sorry, I'm screwing up the camera. Here we go. Yeah, there we go. Okay. Yeah. You're never bothering me at all. Okay. I want you to be successful in this, and I don't want you to get frustrated by it. Okay. And if you need to pause, it's on pause, we can do that too. Okay. I'm very flexible. All right.
Okay. Sounds good.
All right. So I will talk to you Monday then. Okay.
Awesome. Great. Thank you so much.
Okay. You're welcome. You take care now.
You too. Thanks.
Bye-bye.